Light is strange. It is everywhere. It touches everything. And yet when you stop to think about it, its very existence challenges the most basic intuitions we hold about motion. If something has no mass, you would imagine it should be free from all resistance, from all inertia, able to fly with infinite speed across the universe. No weight to drag it down, no burden to slow it, nothing at all to anchor it in space or time. And yet, the truth is far more peculiar. Light is massless, yes, but its speed is not infinite. It moves always at the same exact pace, about 299,792 kilometers per second in vacuum. Never faster, never slower, as though the universe itself set a hard boundary. This is the paradox. If light is weightless, why does it not slip instantly across every distance? Why is there this exact cosmic speed that even the most liberated of particles cannot exceed? Before Albert Einstein, the very idea was baffling. Some thought that maybe light did not really travel, but was instead some sort of vibration carried by an invisible medium called the ether. Others wondered if light could have some hidden weight after all, but experiment after experiment kept showing the same unshakable result. No matter how fast you moved, no matter which direction you measured, light always traveled at the same speed. It did not bend to the expectations of the observer. It did not add to your own motion as ordinary objects do. It seemed to obey its own separate law. Our everyday experience tricks us. When you throw a ball forward on a moving train, the ball carries both your throw and the train's velocity. But shine a beam of light inside that train, and it does not care about the train's motion. Its speed will be the same, whether the train is at rest or rushing through the countryside. Light is indifferent. This indifference reveals something profound, something that forced science to abandon old concepts and craft new ones. Einstein, in 1905, took this stubborn constancy and placed it at the center of physics. Instead of trying to explain it away as an illusion or some measurement error, he said perhaps the universe is built in such a way that light must always move at that speed. The fixed speed of light, rather than being a quirk of photons, became a window into the deeper structure of reality. From that bold assumption came the special theory of relativity, a framework that told us space and time are not separate but woven together into space-time. The paradox of weightless speed is not a trivial curiosity. It is the first sign that our intuitions about motion are only local approximations. In the grand scheme, the universe does not allow infinite velocities, simply because there is no such thing as infinite speed. Motion itself is defined against the constant of light. The finite speed is not a flaw, but a foundation, the scaffolding upon which all causal events unfold. Light moves as it does not because something slows it down, but because this is the pace at which cause and effect are allowed to ripple across the cosmos. And so, to understand why light has no mass yet still has a finite speed, we must accept that our notion of speed needs rewriting. The journey will lead us into the architecture of space-time, into the electromagnetic roots of light itself, into the very meaning of causality. We must peel away our common sense layer by layer until we see that the limit is not imposed on photons, but on the universe as a whole. The paradox is real, but it is also the invitation. It asks us to look deeper and to ask not only how light moves, but why the universe chose this exact way of moving. What we will discover is that speed is not just a number on a dial. Speed is the language of causality, the pulse of space-time, the heartbeat of physics. To unravel why light is bound to this precise value, we must venture beyond appearances, beyond the illusion of weightlessness, and reimagine what motion really means in a universe where even nothingness has laws. Light is not only a physical phenomenon, but also a mirror for our expectations of how reality should behave. The first philosophers to study motion thought of the heavens as a place where perfection reigned, where the rules were different from the flawed world of Earth. The stars seemed eternal, the planets moved with clock-like precision, and light, they imagined, might be some essence that simply revealed these celestial truths. Centuries later, when scientists began measuring carefully, they realized light was not instantaneous. Old Roma, in the 17th century, noticed the moons of Jupiter eclipsing at times that shifted depending on Earth's position. The delay could only be explained if light had a finite speed. Later, more precise experiments confirmed it again and again. But the number they found, though staggeringly fast, was still finite. To imagine something moving with no mass yet finite speed is unsettling. Mass is our familiar anchor. Push an object with mass, and it resists. Remove that mass, and you imagine there should be nothing left to resist. But the equations of nature tell another story. Light, despite having no rest mass, still carries energy. It still carries momentum. It can push on a solar sail. It can knock electrons free in the photoelectric effect. It can bend under the pull of gravity. The absence of mass does not make it empty of influence. Instead, it exists on a razor edge of motion, compelled to travel at exactly the cosmic limit. Not more, not less. The human mind struggles with absolutes. We are accustomed to ranges, to flexibility, to exceptions. Yet light does not grant us that. It moves at the same speed for every observer. If you chase it, you do not reduce its speed. If you race against it, it does not let you close the gap. This strange property is the clue that revealed spacetime's true nature. Because if time and space were rigid, separate backdrops, then speeds should simply add together. The fact that light defies this addition forced Einstein to propose that time itself stretches and contracts depending on motion, that space itself bends and reshapes. Light's constancy was the puzzle piece that demanded a new picture. Consider what this means. When you look up at the stars, you are not seeing them as they are now. You are seeing them as they were when the light began its journey. The nearest star beyond the sun is more than 4 years away at light speed. The galaxies we admire are millions or billions of years distant in light travel time. The fixed speed of light turns the night sky into a time machine. Without this limit, the universe would not carry memory in the same way. It would not stretch history across the heavens. Cause and effect would collapse into instantaneity, robbing us of perspective. Instead, because light has this finite velocity, the cosmos has depth, time has meaning, and history is written across space. The paradox grows deeper when you realize that light does not accelerate. Every other particle with mass must be pushed and gradually speeds up. But light is created already moving at its maximum speed. The moment an atom emits a photon, it is born traveling at that ultimate pace. No gentle start, no ramping up, just immediate motion at the limit. This is unlike anything in our daily world and forces us to rethink what motion island. In truth, for a massless particle, the concept of being at rest has no meaning. Light cannot stand still, even for an instant. To exist without mass is to exist always in motion, locked forever at the speed set by spacetime itself. In this way, the paradox of weightless speed is also the paradox of existence without rest. A photon never experiences time as we do. From its perspective, the moment it is created and the moment it is absorbed could be the same. It is humans, bound by slower clocks and massive bodies, who stretch those moments across years or eons. Light is timeless in its own frame. To us, it is swift but finite. To it, there is no journey at all. This duality, this contrast between perspectives, lies at the heart of relativity. So we arrive at a strange conclusion. The finite speed of light is not a sign of limitation, but of necessity. It is not the photon that is constrained, but the very structure of space-time that defines what motion means. Without this fixed constant, relativity would unravel, causality would collapse, and the very concept of past and future would blur into meaninglessness. The paradox that began with a simple question, why does weightless light not fly infinitely fast, becomes instead a doorway. It reveals that speed is not only about motion through space, but also about the way time itself is woven into the cosmos. And thus, the paradox of weightless speed sets the stage for a new understanding. To move forward, we must stop thinking of light as being slowed by some invisible drag and instead recognize that light moves exactly as fast as space-time allows. This is not a choice of photons. It is not a property of matter. It is a property of reality itself. And to see why, we must next examine how the universe enforces this limit everywhere, for everything, in every possible motion. Light has always seemed to us like a messenger, darting across the void with speed so great that for centuries many thought it must be infinite. Yet, the truth is subtler and more wondrous. The paradox of weightless speed is not a story about a simple beam of light. It is a story about how reality itself refuses to permit infinities. Nature avoids infinities, not by accident, but by design. The finite speed of light is one of the clearest examples of this deep principle. If light were infinite in speed, the very concepts of distance and duration would lose their meaning. Events could not be ordered in time, and cause and effect would collapse into chaos. It is the finiteness of light's velocity that preserves order, rhythm, and the unfolding of history. Imagine a universe where light had no limit. A signal from one end of the cosmos would appear everywhere instantly. There would be no horizon, no waiting, no separation between here and there. In such a universe, every point would know every other point's condition immediately. But that would erase the idea of locality, the idea that things happen in one place and then ripple outward. Locality is essential, because without it, there could be no stars shining into the darkness, no expanding spheres of radiation, no galaxies interacting across cosmic time. Everything would be everywhere at once. Our reality would be unrecognizable. Einstein's insight was not only that light speed is fixed, but that this constancy defines the scaffolding of space-time. Once you accept that light is always observed at the same velocity, no matter how the observer moves, then space and time themselves must flex to accommodate that fact. Clocks tick differently for observers in motion. Lengths contract depending on speed. Simultaneity ceases to be absolute. These are not distortions of perception. They are the real geometry of the universe. The paradox of weightless speed thus resolves not by altering light, but by altering our assumptions about reality. The mystery deepens when you consider that light is not alone in its fate. Any truly massless particle must travel at this same cosmic speed. Gravitational waves, ripples in space-time itself, also propagate at this limit. If there existed any other massless messengers, they too would share this destiny. The speed is not a property of light's structure, but a universal feature of how space-time encodes motion. In this way, the paradox begins to dissolve into a deeper truth. Light is simply the most visible representative of a fundamental law. The paradox also invites a philosophical turn. We are creatures who live far below this cosmic speed. Every atom of our bodies is made of particles with mass. We cannot move at light speed. We cannot escape the drag of inertia. Light, in contrast, exists forever at the horizon of our capability, always faster than us, always unreachable. We chase it in thought experiments, but it always stays just beyond. That unreachability shapes how we imagine knowledge itself. To see is to gather photons that have traveled across space. They come to us with delays, bearing ancient information. We will never catch them, never see the universe as it is now, only as it was. The paradox of weightless speed is therefore also the paradox of knowing. It grants us vision, but with distance and delay. And yet, there is a beauty in this limit. Because light does not move infinitely fast, the universe has a horizon. There are things we cannot see because their signals have not had time to reach us. This horizon is not a failure but a gift. It tells us the age of the cosmos. It defines the observable universe. Without a finite speed of light, we could not measure distance, could not infer the history of galaxies, could not trace the evolution of stars. What appears to be a constraint is in fact a foundation for discovery. As we close this paradox, the picture becomes clear. Light's lack of mass does not free it from all rules. On the contrary, it binds it to the deepest rule of all, the fixed cosmic speed that defines causality itself. Einstein showed us that this is not a speed belonging to photons alone, but the ultimate limit for all events in space-time. Light obeys it not because something holds it back, but because this is what it means to be massless in a universe where space and time are one. The paradox was never truly about light, but about us. It challenged us to see that our old intuitions of motion, drawn from trains and balls and boats, were too shallow. The truth was grander. The truth demanded a rewriting of space and time. And so the paradox of weightless speed becomes our entry point into the deeper mysteries. Why is this speed what it is, neither infinite nor arbitrary? Why does space-time enforce this value instead of some other? To answer those questions, we must move beyond paradox and into principle. We must see how the cosmic limit is not just a curiosity, but the very heartbeat of reality. The next step in our journey is to ask, why is there a cosmic speed limit at all? And how does the universe enforce it so relentlessly? Every story about light eventually becomes a story about the universe itself. The paradox of weightless speed led us to confront the strange constancy of light, and in doing so, it pushed us into Einstein's vision of relativity. But now, a deeper question emerges. If light speed is fixed, then is this merely a property of photons, or is it something written into the fabric of space-time itself? The answer, as relativity shows us, is far more profound. The speed of light is not simply a measurement of how fast particles can move. It is the cosmic speed limit, the maximum pace at which any influence, any ripple of cause and effect, can travel. This limit is not negotiable. No trick of technology, no clever engineering, no rocket more powerful than the last will ever breach it. The reason is not that light is special in some arbitrary sense, but that space-time has rules, and one of those rules is that no signal can exceed this boundary. It is the very structure of reality that enforces this. To imagine something faster is to imagine tearing apart causality itself. Einstein's special relativity rests on two postulates. The first is that the laws of physics are the same for all observers in uniform motion. The second is that the speed of light in vacuum is the same for all such observers, no matter how they move relative to one another. From these two assumptions, all the strange and wondrous consequences follow. Time slows for fast travelers. Lengths shrink along the direction of motion. Simultaneity becomes relative, so that what is now for one observer may be past or future for another. But through it all, the speed of light remains unchanged, the anchor in the shifting sea of perception. What makes this so important is that light speed is not just about light, it is about causality. If a signal could outrun light, then one observer might see an event before its cause. Cause and effect would become scrambled, and paradoxes would multiply. The universe forbids this by setting a hard ceiling on the speed at which information can propagate. That ceiling is the constant we call c, roughly 299,792 kilometers per second. Light, being massless, simply rides this cosmic limit, not by choice, but by necessity. To understand this, picture space-time as a vast four-dimensional fabric, woven from 3 dimensions of space and 1 of time. In this fabric, the possible paths that particles can take are divided into categories. Massive particles move slower than c, tracing time-like paths. Massless particles move exactly at c, tracing null paths. And hypothetical faster than light particles, which we have never observed, would trace space-like paths. But space-like paths break causality. They allow communication into the past. They allow violations of cause and effect. And so the universe never permits them. This structure gives us the famous light cone. From any event in space-time, draw all possible directions light could travel. That cone marks the boundary of what can be influenced and what cannot. Inside the cone, events can be causally connected. Outside, they are forever out of reach, unable to affect or be affected. The light cone is the most elegant picture of the cosmic speed limit. It is not merely about photons, it is about the limits of possibility itself. When we say light moves at c, we are not really measuring the properties of light alone. We are measuring the deepest characteristic of space-time. C is the speed of causality, the ultimate rate at which the universe allows events to unfold. Whether the messenger is a photon, a gravitational wave, or any massless particle yet undiscovered, the rule is the same. Move slower than c, and you are bound to time-like journeys. Move at c, and you exist forever on the horizon of causality. Attempt to move faster, and the universe denies your path. It is easy to mistake c for just another number, another constant in the equations of physics. But it is not like the boiling point of water or the density of gold. It is not an arbitrary fact that could be different in the same universe. It is the very scaffolding of reality. The limit does not apply to light alone, but to everything. Nothing, with mass, may reach it. Nothing at all may exceed it. Thus, the paradox of weightless speed transforms into a revelation. Light moves at c, not because it chooses to, not because something restrains it, but because this is the universal limit, the line drawn into the fabric of space-time. Light is the herald of that limit, the particle that shows us where the possible ends and the impossible begins. And so the cosmic speed limit is not a technical curiosity, not a laboratory trick, but the heartbeat of reality itself. To ask why light does not move faster is to ask why causality is preserved. To imagine exceeding this limit is to imagine a universe where effect might precede cause, where history could be rewritten, where paradoxes would explode into every corner of existence. Our universe does not allow that. The speed of light is finite, and it is final. It is the speed at which reality itself insists that change may propagate. The realization that c is not about light alone, but about the very nature of causality, changes everything about how we see motion. In our everyday lives, we are used to adding speeds together. A car drives down a road at 100 kilometers per hour, and inside it a passenger throws a ball forward at 20 kilometers per hour. To the person standing on the roadside, the ball appears to move at 120 kilometers per hour. This is ordinary, intuitive, and familiar. Yet light refuses this logic. Shine a flashlight from that same moving car, and the beam does not appear to travel faster to the person outside. It still moves at 299,792 kilometers per second. Even if the car itself were racing near that cosmic speed, the beam would not add one more increment. It would still move at c, unaltered, unyielding. This simple but stubborn fact means that space and time themselves must be flexible, for otherwise the addition of speeds would ruin the constancy of c. If space and time were absolute, the beam would indeed go faster for some observers. Since it does not, the absolutes must go. In their place, relativity emerges. To preserve the limit, clocks must tick differently for observers in motion, and rulers must shrink. What seems like an illusion of perspective is in fact the deep geometry of space-time. Time dilation and length contraction are not tricks of perception. They are the way the universe balances its books to keep the speed of light constant for all. From this follows the inescapable truth that no massive object may reach c. As it accelerates closer, its energy increases without bound. Each increment requires more and more energy until at the limit, the demand becomes infinite. This is why no spaceship, no matter how advanced, can ever be accelerated to light speed. The barrier is not technological but fundamental. The mass of the ship ties it to time-like paths, where speeds are always less than c. Only massless particles are granted the privilege of moving at the cosmic limit, and they do so automatically from the moment of their creation. The cosmic speed limit also shapes the map of the universe. Because nothing can travel faster than c, there are regions of space forever beyond our reach. Galaxies so distant that their light has not yet had time to arrive are invisible to us. They may exist, but they are outside our observable universe. Even if we waited for billions of years, some of them would remain forever hidden because the expansion of space carries them away faster than light can close the distance. This is not a violation of the limit, because it is not objects moving through space faster than light, but space itself, stretching. Still, the effect is the same. There are cosmic horizons beyond which no message can ever arrive. The cosmic speed limit is therefore not just about motion, but about knowledge. It dictates what we can learn, what we can see, and what we can influence. It defines the boundary between the known and the unknowable. When astronomers peer deep into space, they are peering deep into time, but only as far as light has been able to travel since the birth of the universe. Beyond that lies a realm that will remain forever inaccessible, walled off by the finite velocity of causality. The speed of light is not only the limit of motion, but the limit of awareness itself. This realization is humbling. It tells us that no matter how advanced our science becomes, no matter how powerful our machines grow, there are frontiers we cannot cross. The laws of physics grant us extraordinary power to predict, to explore, to manipulate, but they also impose absolute boundaries. The cosmic speed limit is one of those boundaries. It is a reminder that the universe is not infinitely malleable. It has laws that cannot be negotiated away. And yet, within those laws lies beauty. The constancy of c gives rise to relativity, which in turn explains the unity of space and time. It shows us that the universe is not a static stage, but a dynamic fabric where motion reshapes geometry itself. The very strangeness of relativity arises from the effort to preserve that constant speed. And in preserving it, the universe preserves causality, order, and meaning. Light's finite speed is not a weakness of nature, it is its safeguard. When Einstein first proposed this, many resisted. It seemed absurd that time could slow, or that lengths could contract. But experiment after experiment confirmed it. Muons, unstable particles created in the upper atmosphere, live longer when moving at near light speed, just as relativity predicts. Atomic clocks flown around the world tick at slightly different rates depending on their motion, matching Einstein's equations. Particle accelerators confirm that as particles approach c, the energy required to push them further rises steeply toward infinity. Reality has spoken, and it speaks the language of relativity. Thus, the cosmic speed limit is not a quirk, but a cornerstone. To question why light does not move faster is to misunderstand the law. Light does not choose a speed, it embodies the universal limit. The question is not why it is restricted, but why the universe itself is structured with such a bound. And that question leads us deeper still, into the geometry of space-time itself, into the way motion is inscribed in the very shape of reality. The cosmic speed limit is most clearly seen when we imagine the geometry of space-time itself. Picture a sheet stretched out in every direction, not flat but four-dimensional, woven from the three coordinates of space and the one of time. In this fabric, every event is a point. From that point, the possible futures spread outward in the shape of a cone, the light cone, its sides marked by rays traveling at c. Inside the cone are all the events that could be reached or influenced by signals moving slower than or equal to light. Outside the cone lie events forever beyond reach, separated not by distance alone, but by the very order of causality. This is the deep meaning of the speed of light. It is the slope of reality, the angle that separates possible futures from impossible ones. When you walk down the street, you are tracing a path inside your light cone, moving slower than c, bound by mass and inertia. When a photon is emitted from the sun, it travels exactly on the cone, racing at the boundary of possibility. Nothing may pass outside. To do so would be to send information backward in time, to allow causes to arrive after their effects, to tear the sequence of reality apart. The cosmic speed limit is not arbitrary. It is the law that makes time meaningful, that ensures events have an order, that the arrow of causality is preserved. This also reveals why the limit is so difficult to grasp intuitively. Our senses evolved for a world where speeds are low compared to c. In daily life, the difference between 100 kilometers per hour and 120 kilometers per hour is real and measurable. But when we climb towards c, relativity takes hold. At 90% of light speed, time for the traveler slows to about half compared to someone at rest. At 99%, the effect is even stronger. Approaching the cosmic limit, time nearly freezes for the traveler, while to them the universe outside seems flattened in the direction of motion. These distortions are not tricks of the eye. They are reality itself, reshaping under the weight of the cosmic speed limit. Consider also the role of mass. For anything that carries mass, rest is always possible. You may sit still, you may move slowly, and you may accelerate, but the limit always bars you from C. For anything without mass, rest is impossible. A photon can never stop, not even for a moment. To exist without mass is to exist in perpetual motion, racing always at C. There is no in-between. This sharp division is a direct consequence of the geometry of space-time. Time-like paths belong to the massive, null paths to the massless. The universe tolerates no exceptions. The cosmic speed limit also ties together forces once thought separate. Maxwell's equations, which describe electricity and magnetism, predict waves of oscillating fields that travel at a fixed velocity. That velocity, derived from constants of the vacuum, turns out to be exactly c. When Einstein examined relativity, he realized that this was no coincidence. The same constant that limits the speed of electromagnetic waves also governs causality itself. What began as a property of light became the universal property of space-time. So when we say light travels at c, we are really saying something deeper. We are saying that c is the defining feature of how space and time interweave. Photons are not privileged, but they reveal the limit most clearly because they are forced to move at it. Gravitational waves, confirmed a century after Einstein predicted them, also move at c, proving again that the limit is woven into reality itself. In this light, the question of why light cannot move faster becomes almost meaningless. It is like asking why two parallel lines do not cross. The answer is that the rules of geometry define what is possible. In space-time, the rules declare that nothing may move faster than c. Light, being massless, simply has no choice but to trace the limit exactly. The cosmic speed limit is therefore not about restraint, but about definition. It is the way the universe defines motion, time, and causality. Without it, we would live in a world where events had no order, where cause could follow effect, where paradoxes destroyed consistency. Instead, we live in a universe where time flows with coherence, where the fabric of space-time holds firm, where the light cone marks the boundary of what can be known and what can be done. And yet, a new question arises. Why is the value of c what it is? Why 299,792 kilometers per second and not some other number? If c is the scaffolding of reality, what sets its height? To answer that, we must dig deeper, beyond relativity, and into the electromagnetic constants of the vacuum, the hidden settings of the universe that give rise to the cosmic speed limit. The cosmic speed limit is not a rule tacked onto nature like a posted sign along a road. It is not a restriction applied from the outside. It is something far more profound. The universe is built in such a way that no object, no signal, no flicker of causality can exceed this limit. The enforcer is not light, nor electromagnetism, nor any hidden drag, but space-time itself. The very geometry of reality defines the boundaries of motion. To see this, we must imagine space-time not as a backdrop, but as a participant. In Newton's picture, space and time were stage and clock. Space was an infinite container, empty and silent, within which objects moved. Time was a steady rhythm, unchanging and absolute. In such a world, it would make sense to think of speed as something with no inherent cap. If you could remove resistance, why not go infinitely fast? But Einstein showed us this picture is false. Space and time are not separate and rigid. They are interwoven into space-time, and space-time has structure. That structure determines what paths particles may take. In this structure, motion follows geodesics, the straightest possible lines through curved geometry. Massive particles trace time-like geodesics, paths that always remain below c. Massless particles trace null geodesics, paths that lie exactly at c. No path exists that corresponds to motion faster than c, because the geometry does not allow it. In this way, the speed limit is not a rule imposed on photons, but an intrinsic feature of the fabric through which everything moves. Space-time itself dictates what is possible. Consider the analogy of the Earth's surface. Draw a line of longitude from the equator to the pole, and you have traced a geodesic, the straightest possible path on the sphere. No matter how you walk, You cannot step off the surface of the Earth without leaving the geometry itself. In the same way, no matter how you try to accelerate, you cannot step outside the causal structure of space-time. The null geodesics define the maximum slope of motion, and that slope is c. This enforcement is subtle but absolute. In the equations of relativity, the metric of space-time describes how distances and durations are measured. The speed of light emerges naturally from this metric as the conversion factor between space and time. It is not added into the equations by hand. It arises from the very shape of reality. That is why c shows up everywhere, from electromagnetism to gravity, from quantum field theory to cosmology. It is the thread that runs through all laws, because it is woven into the fabric on which the laws are written. This is why attempts to imagine faster-than-light travel stumble on paradoxes. A warp drive or a tachyon would require paths through space-time that the geometry does not allow. To sketch them is to sketch contradictions, where signals loop backward, where events lose their order. It is not simply that technology is insufficient. It is that the geometry of reality itself forbids such trajectories. The enforcer is not a force we might one day overcome, but the very definition of the stage upon which existence unfolds. From this perspective, light's behavior is no longer puzzling. A photon does not move at c because of some property of itself. It moves at c because the geometry of space-time has decreed that any massless particle must trace null geodesics. A photon is simply an instance of this law, a visible representative of the deeper truth. The speed of light is not about light at all. It is about space-time's architecture, and here the paradox of weightless speed dissolves. Light cannot go faster, not because it is held back, but because there is no such thing as faster within the geometry of reality. The null path is the limit. To imagine something beyond is to imagine leaving space-time itself, stepping outside the very definitions of distance and duration. In this sense, space-time is the true enforcer, not as a policeman imposing penalties, but as a map that defines what paths even exist. Yet, one mystery remains. Why is the slope of these null geodesics exactly what it is? Why does space-time enforce this particular value of c rather than another? If geometry is the enforcer, then something deeper must have set the geometry's scale. To answer that, we must look into the electromagnetic constants of the vacuum, the hidden settings of the universe that determine how fast light can travel. Space-time enforces its rules without compromise. The notion of a particle choosing its speed is a misunderstanding born of our everyday lives. A car may go slower or faster along a road, and a runner may choose to accelerate or stop. We are tempted to imagine that light, being weightless, could take any speed it wished. But photons are not drivers on a road. They are not objects moving within a backdrop of fixed space and time. They are excitations riding on the very geometry of space-time, and that geometry admits only one possible velocity for massless entities. This becomes clearer when we look at the mathematics of relativity. The interval, the fundamental measure of space-time separation, is given by a balance of time and space coordinates. For time-like paths, where massive objects travel, the interval is positive. For space-like paths, which correspond to faster-than-light trajectories, the interval is negative, and no real particle can follow such a path. For null paths, the interval is 0. That 0 is the fingerprint of massless motion, and it corresponds exactly to the speed of light. It is not a preference. It is the geometry dictating what kind of path is possible. Imagine a beam of light leaving a distant galaxy billions of years ago. It has no freedom to lag or to race ahead. Its entire path is predetermined by the structure of space-time. Along the way, the expansion of the universe stretches its wavelength, redshifting it into lower energy. Gravity bends its course around massive clusters of matter. Yet through all these changes, its local speed remains c, because the null geodesic is the only line it can trace. Space-time is the enforcer, and the photon is merely the traveler bound to that path. The same is true for gravitational waves. When two black holes collide, they send ripples across the universe. Those ripples travel not through space, but as oscillations of space-time itself. And yet, they too move at sea. This was confirmed when detectors on Earth observed gravitational waves from a neutron star collision, followed by a burst of light, arriving almost simultaneously. Two very different messengers, one an oscillation of space-time, and the other a stream of photons, but both racing at the same cosmic speed. This was not coincidence. It was space-time revealing its deepest law, that all causal messengers, no matter their nature, must move at sea. The enforcement is so strict that it shapes even the concept of possibility. If you stand at a point in space-time and draw your light cone, you divide reality into three regions. Inside the cone are the events that you can influence, or that can influence you. On the surface of the cone are the events connected by light or other massless signals. Outside the cone are the events forever disconnected, unreachable, no matter how much time passes. This division is absolute. It does not depend on who you are, where you are, or how you move. It is written into the geometry itself. This is why faster-than-light ideas run into paradoxes. A tachyon, a hypothetical particle always moving faster than c, would cut across the light cone and connect events that should remain disconnected. In some frames of reference, it would even appear to move backward in time, delivering information before it was sent. The result is contradiction, where cause follows effect, where the arrow of time splinters. The geometry of space-time does not permit such travelers, not because they are forbidden in a legalistic sense, but because their paths do not exist in the map of reality. The enforcer does not punish violators, because there are no violators. There are only allowed paths and impossible ones. Just as one cannot draw a triangle with 4 corners, one cannot trace a trajectory faster than c. The geometry makes it meaningless from the start. Light and other massless messengers ride the edge of possibility, and massive objects trace slower curves. These are the only categories that space-time admits. The elegance of this enforcement lies in its inevitability. There is no force dragging on photons, no hidden medium slowing them down. There is only the geometry, which makes c the translation factor between space and time. In this geometry, moving at c is the natural state of the massless. Any other speed would be a contradiction in terms. Space-time enforces the law not by intervention, but by definition. And yet, the number itself, that exact value of nearly 300,000 kilometers per second, calls out for explanation. Why not double? Why not half? Why not infinite? Geometry tells us that c must exist, but it does not tell us why it has that specific magnitude. For that, we must dig deeper into the electromagnetic structure of the vacuum, where constants of nature fix the value of c itself. Space-time is the great sculptor of motion. Once you accept that its geometry determines the possible paths of particles, the cosmic speed limit feels less like a rule imposed from above and more like a natural consequence of how reality is shaped. What we call the speed of light is simply the angle at which space-time divides events into cause and effect, possible and impossible, connected and forever isolated. The photon has no freedom to move faster because there is no such direction in the geometry. Faster-than-light motion does not exist as an option, in the same way that walking north and south at the same time does not exist on the surface of the Earth. This is why physicists say light follows null geodesics. A geodesic is the straightest possible path through a curved surface. On the Earth, it is a great circle. In space-time, it is a trajectory dictated by the metric, the mathematical rule that defines distances and durations. A null geodesic is one with zero space-time interval, a path along which no proper time elapses. This is the path that massless particles must follow. They cannot bend into time-like curves because they lack mass, and they cannot wander into space-like paths because those are not physically real. They ride the razor edge of geometry, always and only at c. In this picture, the paradox of weightless speed becomes almost poetic. Light moves, as it does, not because of what it is, but because of where it lives. It inhabits the fabric of space-time in such a way that its only possible motion is at the cosmic limit. The enforcer is the universe itself, silent and absolute. When we see a photon cross the void, When we detect a gravitational wave ripple in our detectors, we are not watching something strained by a law. We are watching reality express its geometry, and yet the human mind resists. We are used to imagining rules as external, as boundaries that can be challenged or broken. We think of speed limits on roads, laws in courts, rules in games. These can all be violated, sometimes at great cost, but violation is possible. The cosmic speed limit is nothing like that. It is not a rule, but a definition. To ask why light cannot move faster is like asking why circles are round. The question collapses into the truth that the geometry itself leaves no alternative. This insight should not diminish our wonder but heighten it. The universe is not an arbitrary assembly of forces, but a coherent whole. Space-time, matter, energy, light, gravity, all are interwoven in a single fabric. The fact that geometry enforces motion at sea tells us that the universe is not chaotic but ordered. It has principles that hold everywhere, from the smallest scales of particles to the largest scales of galaxies. Still, the precise value of c remains mysterious. Geometry explains why there must be a limit, but it does not explain why the limit is this particular number. That value is set by the properties of the vacuum itself, by the constants that describe how electric and magnetic fields interact. The permeability and permittivity of free space combine to define c. These are not arbitrary, but neither are they yet derived from deeper principles. They are the settings of the universe, values we measure, but do not yet explain. Thus, space-time is the enforcer of the limit, but the limit's magnitude comes from the underlying physics of the vacuum. Together, they form the complete picture. Geometry tells us there must be a maximum speed. Electromagnetism tells us what that speed island. To understand why c has its value, we must now move from geometry into the physics of fields, from space-time into the structure of the vacuum itself. Only then can we ask the deeper question, why this number and not another? Space-time enforces the cosmic speed limit with unyielding authority, but geometry alone does not tell us why the limit is set at the particular value we measure. The universe could, in principle, have been written with different numbers in its equations, different balances of forces, different constants underlying the same geometry. And so the question arises, why is c what it is? Why nearly 300,000 kilometers per second, and not some other value? The key lies not only in relativity, but in the physics of the electromagnetic field itself. Before Einstein revealed the deeper meaning of light's constancy, James Clerk Maxwell had unified electricity and magnetism into a single set of equations. From those equations, a startling prediction emerged. Electric and magnetic fields could generate one another, oscillating back and forth, creating waves that propagate through space. When Maxwell calculated the speed of those waves, he found a number determined by the electric permittivity of free space and the magnetic permeability of free space. The result was precisely the value measured for the speed of light. This was no coincidence. It was a revelation. Light was not a mysterious phenomenon, traveling through an invisible ether. It was an electromagnetic wave, its speed set by the constants of the vacuum. The permittivity of free space describes how electric fields interact with the vacuum, how charges create and respond to those fields. The permeability of free space describes how magnetic fields behave, how currents and loops of charge respond to magnetism. Multiply these constants together in the right way, and their combination fixes the speed at which electromagnetic waves travel. That value is c. The speed of light is not arbitrary, but emerges from the electromagnetic properties of the vacuum itself. In this sense, c is not simply a number tagged onto space-time. It is a bridge between geometry and field theory, between relativity and electromagnetism. The vacuum, which we imagine as empty, is not truly empty. It has structure. It has properties that dictate how fields behave, and from those properties comes the cosmic speed limit. The void itself defines the pace at which light and causality move. Now imagine a universe with different constants. If the permittivity or permeability of free space had different values, then c would be different. Light might travel slower or faster. The geometry of relativity would still enforce a maximum speed, but the magnitude of that speed would change. Time, dilation, and length contraction would still occur, but their scale would be altered. The horizons of the observable universe would shift. The balance of forces in atoms might vary, and chemistry itself could be different. The very possibility of life might depend on these values being what they are. Physicists sometimes call this the fine-tuning problem. The constants of nature are not explained by deeper theory, at least not yet. They are measured, written down, and accepted as the foundation of all else. Why they take the values they do remains an open question. Some propose that deeper unifying laws will eventually derive them. Others suggest that perhaps many universes exist, each with different constants, and we find ourselves in one where the numbers happen to permit complexity and life. Whatever the ultimate answer, the fact remains that the speed of light is determined not only by geometry, but by the physical properties of the vacuum, the hidden settings of the cosmos. The beauty of this revelation is that it ties together the grand and the small. On the largest scales, C defines the structure of space-time and causality. On the smallest scales, C emerges from the constants that govern how charges and fields behave. The cosmic speed limit is thus both a geometric boundary and an electromagnetic consequence. Light reveals it not by whim, but by necessity. And yet, the question presses further. If C arises from the vacuum's properties, then what gives the vacuum those properties? Why does empty space permit fields to behave as they do? Here lies the frontier, where physics reaches beyond what is known into speculation. Perhaps deeper symmetries, hidden layers of reality, or quantum structures of space-time itself set the values. Perhaps C is not merely a constant, but a reflection of something more fundamental, something we do not yet see. To move forward, we must accept that the speed of light is both a consequence of relativity and a fingerprint of the vacuum. Geometry enforces that there must be a maximum speed. Electromagnetism reveals what that speed island together. They explain why light moves at C and not another value. But there is more to uncover, because C is not only the velocity of photons, it is the velocity of causality, the maximum rate at which information itself can move. To understand why that matters, we must turn from fields and geometry to the concept of information, the hidden current flowing through the laws of physics. The discovery that the speed of light is determined by the electromagnetic properties of the vacuum was one of the great triumphs of 19th century science. When Maxwell wrote down his equations, he was not searching for a universal speed limit. He was unifying electricity and magnetism, showing that the two forces were facets of one reality. Yet hidden inside his mathematics was a number, and that number turned out to match the measured speed of light. It was as if the equations themselves were whispering a cosmic truth, that the structure of space was encoded in the way fields move through the vacuum. This result was astonishing because it showed that what we call empty space is not truly empty. Even in the absence of matter, space has properties. The vacuum responds to electric fields with a certain elasticity, described by its permittivity. It responds to magnetic fields with a certain stiffness, described by its permeability. These properties are as real and measurable as the density of a metal or the viscosity of a fluid, and when they are combined, they set the pace of electromagnetic waves. That pace is what we call C. To appreciate the profundity of this, imagine once again that the constants were different. Suppose the permittivity of free space were larger. Electric fields would spread more sluggishly, electromagnetic waves would travel more slowly, and C would be smaller. Relativity would still hold, but the distortions of time and space would occur at lower speeds. The universe would feel tighter, more constrained, and the distances light could cover in a given time would shrink. If the permeability were different, magnetic effects would shift, altering the balance of forces in atoms and molecules. Chemistry itself might change, and with it, the possibility of life. The very fabric of existence depends delicately on these constants being what they are. Physicists have long pondered whether these constants could have been otherwise. Are they fixed by some deeper law, or are they arbitrary settings, like dials on a cosmic machine? This touches on the idea of a multiverse, a vast landscape of possible universes, each with different values of the fundamental constants. In most, conditions would be sterile, incapable of supporting complex structures. In a rare few, the values would align in such a way that atoms could form, stars could burn, and life could arise. We, of course, find ourselves in one of those rare universes because only there could observers exist to ask the question. This is not a settled answer, but a suggestion, a way of framing the puzzle. The fact remains that we do not know why C has its value. We know how to calculate it from the measured constants, and we know how it shapes the universe. But the deeper reason, the ultimate origin of those constants, remains hidden. Perhaps it lies in the unification of forces at energies we cannot yet reach. Perhaps it lies in the quantum foam at the smallest scales, where space-time itself may have a discrete structure. Perhaps it is simply a fact, a brute reality with no further explanation. Still, the unity revealed by Maxwell and Einstein is breathtaking. Electromagnetism and relativity, two seemingly separate domains, converge on the same constant. C is both the speed of light and the speed limit of space-time. It arises from the vacuum and yet defines the geometry of the universe. It is at once a product of fields and a guardian of causality. This duality gives C a special status among the constants of nature. It is not merely another number, it is the key that ties together disparate realms of physics. And so the question of why C has its value remains one of the most profound in science. It is a question that bridges electromagnetism, relativity, quantum theory, and cosmology. To ask it is to probe the very foundation of reality. Yet perhaps the most striking aspect is that C is not simply the speed of light. It is the speed of information, the maximum rate at which any influence can move through space-time. To understand the full meaning of C, we must shift our focus from fields and geometry to causality itself, to the flow of information that defines the boundary between the possible and the impossible. The constants of the vacuum give us the number, and relativity gives us the meaning, but together they still leave us standing at the edge of a mystery. Why is reality tuned so that C has this value? It is tempting to think of it as arbitrary, but when you look closely, you realize that the value of C is not isolated. It ties together with other constants of nature in delicate balance. The strength of electromagnetism, the mass of the electron, the charge of the proton, and the structure of quantum fields all intertwine with the value of C. Change it, and the universe changes with it, not only in degree, but in kind. For example, consider atomic structure. The energy levels of electrons in atoms depend on the fine structure constant, a dimensionless number built from the electron charge, Planck's constant, and C. If C were different, this constant would shift, and the very chemistry that builds the periodic table could collapse. Stars might not form as they do. Nuclear reactions might not proceed with the same balances. Even if space-time still enforced a maximum speed, the patterns of matter would be alien, perhaps lifeless. The value of C, through its connection to other constants, helps determine the richness of structure in the cosmos. It is possible that deeper theories, perhaps a grand unification of forces, will one day show that C could not have been otherwise. In such a picture, the constants we measure today would be derived from deeper principles, perhaps emerging inevitably from the mathematics of higher symmetries or from the shape of extra dimensions. But until that day comes, we live with the fact that C's value is both measured and mysterious. We know what it is, we know what it does, but we do not yet know why it is so. This is part of what gives physics its tension between humility and ambition. On one hand, we are humbled by the realization that the constants may simply be facts we must accept, written into the universe, without explanation. On the other hand, we are driven by the ambition to dig deeper, to find patterns beneath the surface, to believe that nothing so fundamental could be entirely arbitrary. C sits at the heart of that tension. It is at once explained and unexplained, understood in function, but not in origin. And yet, Even without final answers, the consequences are extraordinary. Because C has its value, the universe has its horizons. The cosmic microwave background radiation stretches across the sky because photons took billions of years to reach us. Supernovae shine as delayed beacons, telling us stories from across time. Gravitational waves ripple outward at sea, announcing collisions of black holes in distant galaxies. Every piece of cosmic information we receive is framed by the speed of light. If C were infinite, the sky would hold no history. If C were slower, the universe would be darker, smaller, less connected. As it is, the universe has exactly the right depth to hold memory, exactly the right scale to allow galaxies and life to exist. In this way, the question of why C has its value becomes philosophical as much as physical. It asks not only about numbers, but about meaning. Why is there a universe that allows memory, causality, and order? Why do the constants align so that light reveals the past and carries information across the void? Whether the answer is deeper physics or cosmic coincidence, the fact remains: C is both the measure of speed and the measure of possibility. It sets the rhythm of reality. And so, as we leave behind the question of why C has this number, we turn to the next layer of understanding. C is not only about light, not only about electromagnetism, not only about geometry, it is about information itself. For the speed of light is the speed at which information moves, the upper bound of causality. To understand its true meaning, we must step beyond fields and constants and ask what it means for the universe to limit the flow of information. That is the deeper story waiting to be told. From the beginning, light has been our messenger. Every star we see, every galaxy revealed through a telescope, every corner of the universe we explore through astronomy comes to us as light. But as profound as that is, the true significance of light lies not only in illumination, but in information. The speed of light is the maximum speed at which any information can travel. It is the pulse of causality itself, the tempo at which the universe allows knowledge to spread from one point to another. To understand this, imagine sending a signal. Perhaps it is a flash of light, perhaps a pulse of radio, perhaps even a gravitational wave produced by colliding stars. In every case, the message cannot move faster than C. This is not a quirk of the technology, but a fundamental law. Information is bound by the same geometry that binds particles. The light cone we have traced in thought experiments is not just a boundary of motion, it is the boundary of communication. Inside the cone, information can flow. Outside the cone, no message can ever arrive. This restriction is more than technical. It preserves the order of reality. If information could move faster than C, then one observer might see an effect before its cause. A message might arrive before it was sent. Paradoxes would bloom, undermining the very idea of time. Cause and effect would be scrambled, and the fabric of reality would lose coherence. Relativity prevents this chaos by locking the flow of information to C. The universe enforces consistency not by will but by geometry. In physics, this principle is called causality. Causality is not a philosophical preference, but a physical requirement. Events must unfold in an order that all observers agree preserves the link between cause and effect. Relativity achieves this by ensuring that no signal outruns light. What seems at first like a limit becomes, on reflection, the guarantee of coherence. The speed of light is the speed of causality, the universal safeguard against paradox. Consider what happens when we observe distant galaxies. Their light takes millions or billions of years to reach us. That means the information we receive is delayed, but it is consistent. The galaxy cannot influence us until its signals arrive. We cannot influence it until our signals arrive. This mutual delay is frustrating for the imagination, but it is essential for order. The finite speed of light structures the universe into webs of influence that unfold in time. Without it, all events would collapse into simultaneity, and causality would lose meaning. Even in quantum mechanics, where probabilities and uncertainties play their games, the speed of information remains bound by c. Quantum entanglement creates correlations between particles separated by great distances, but those correlations cannot be used to send usable information faster than light. The no-communication theorem of quantum theory makes this explicit. The universe remains consistent. Even where strangeness abounds, causality is preserved. Seen in this way, the speed of light becomes more than a number. It becomes the very grammar of reality, the rule that allows stories to unfold in sequence. Without c, there would be no before and after, no memory and anticipation, no history and future. Light, in moving at c, is not only a particle or a wave, it is the boundary marker of time itself. And so the paradox of weightless speed reaches its most profound resolution. Light does not move infinitely fast because infinity would erase causality. It moves at exactly c, because c is the speed at which information itself may travel. This is the cosmic compromise. Finite speed allows coherence, while constancy allows relativity. What feels like a limit is in truth the foundation of possibility. Yet one question still lingers. If the speed of light is the speed of information, what would happen if that limit could somehow be broken? Would the universe unravel? Would paradoxes arise? Could cause and effect collapse into absurdity? To explore that possibility, we must test the very edges of imagination, where physics brushes against speculation, and ask what it would mean if information could move faster than light. If the speed of light is the speed of information, then the boundary it creates is as much philosophical as it is physical. It shapes not only what signals can reach us, but what it even means to know. Information is the thread that connects cause to effect. Without it, events would be disconnected fragments. With it, the universe becomes a story, written in the exchange of signals and the unfolding of influence. The speed of light ensures that this story has structure. It enforces the arrow of time by binding information to a pace that can never be exceeded. Think of the simple act of conversation. When two people speak face to face, sound travels at hundreds of meters per second through air, carrying words from one to the other. Replace sound with light, and the signals move faster, nearly 300,000 kilometers per second in vacuum. Yet, even at that immense velocity, there is still delay. When you look at a friend standing across the room, you see them not exactly as they are now, but as they were a tiny fraction of a second ago. The delay is imperceptible, but it is real. Stretch the distance, and the effect becomes undeniable. Look at the moon, and you see it as it was more than 1 second ago. Look at the sun, and you see it as it was 8 minutes ago. Look at distant galaxies, and you are gazing into epochs long past. The finite speed of light is what makes the universe a time machine. It carries the past into the present, allowing us to reconstruct history, but never to see the now. This delay is not a weakness, it is what makes knowledge possible. If light were infinite in speed, then information from every corner of the universe would arrive instantly. There would be no separation of past and present, no distance to cross, no sequence to preserve. Reality would be a blur of simultaneity, a chaos of events with no temporal order. It is the limit that saves us from that confusion. The slowness of light, on cosmic scales, is what allows us to read the history of the stars, to measure the age of the universe, to trace the evolution of galaxies. Every telescope is a time machine precisely because information does not arrive all at once. Physics reveals this limit again and again. In relativity, no observer can send or receive information outside their light cone. In quantum field theory, influences propagate no faster than c, preserving locality, even in the face of quantum uncertainty. In thermodynamics, entropy increases as information disperses, carried at finite speed through signals and interactions. Across every framework of physics, the same rule appears. C is the guardian of information. There are those who dream of breaking the limit. Science fiction abounds with faster-than-light communication, with ships sending instant messages across the stars. But the equations of physics resist. If such signals were possible, then in some frames of reference, they would travel backward in time. A message could be received before it was sent. A warning could arrive before the danger, creating loops of paradox that destroy consistency. Relativity does not forbid faster than light travel, merely out of stubbornness. It forbids it because without the limit, causality collapses. The protection of causality is more than a technical detail. It is what makes science itself possible. To test a theory, to perform an experiment, to connect cause and effect, requires that the universe preserve temporal order. If signals could outrun light, the link between observation and cause would break. Knowledge itself would be impossible. Thus, the speed of light is not simply the limit of information, it is the foundation of knowing. And so, the recognition grows clearer. The constancy of c is not a rule about photons. It is the law that preserves the story of reality. Information moves at c because c is the heartbeat of causality. It is the tempo of the universe, the rhythm that ensures events unfold in sequence. Without it, the cosmos would be unrecognizable. With it, the cosmos has memory, order, and meaning. Imagine, for a moment, a universe where information could outrun light. A signal leaves one planet and arrives at another before the light from the same event even begins its journey. At first, this sounds like an engineer's dream, a triumph over distance. But relativity forces us to see it differently. In one frame of reference, the signal arrives before it is sent. In another, the cause follows the effect. The chain of reasoning unravels, and paradox creeps in. Could you warn your past self of an accident? Could you send knowledge of tomorrow's discoveries back to yesterday? Such possibilities are not just strange, they are inconsistent. They break the very logic that allows a universe to exist with order. This is why relativity guards the speed of light with such absolute consistency. The limit is not about the mechanics of light beams or the properties of photons. It is about the preservation of time's arrow. Information carried faster than light would let events influence the past. Space-time would splinter into contradictions. Some observers would watch histories that others would deny. Reality itself would fracture. By fixing c as the maximum speed, the universe shields itself from incoherence. In the laboratory, no evidence has ever contradicted this rule. Every attempt to send signals faster than light, whether through clever manipulation of media or exploitation of quantum entanglement, has failed. When scientists slowed light in Bose-Einstein condensates, reducing its group velocity to mere meters per second, the fundamental limit of c remained untouched. The pulse of information did not exceed the cosmic limit. When entangled particles displayed correlations across vast distances, they did so without allowing communication faster than light. Nature allowed strangeness, but preserved causality. It is this consistency that makes the speed of light so extraordinary. It is not only about motion, it is about logic. It is the safeguard against paradox, the barrier that maintains the coherence of history. Imagine living in a universe without such a barrier. Every event could ripple across time without order. Cause could be undone by effect. Memory could rewrite itself endlessly. Science, knowledge, and even consciousness might dissolve into chaos. The finite speed of information is what prevents that nightmare. It is what keeps the universe intelligible. And so the deeper meaning of c emerges. It is not merely the speed of photons in a vacuum. It is the rate at which reality maintains consistency. It is the limit that ensures events unfold in a story rather than a scramble. Light, in moving at c, simply reveals the bound that space-time already demands. Gravitational waves, neutrinos, and any massless particle must obey the same. C is the pulse of causality, and causality is the skeleton of reality. Thus, when we ask why light cannot go faster, we discover that the question is larger than light. The answer is that faster than light motion would unravel causality itself. The speed of light is not only a boundary of physics, but a boundary of logic. It is the universe's way of saying that time must flow forward, that stories must have order, that knowledge must grow within the bounds of coherence. To break C would not be to move quickly, It would be to move outside of reason. And here we reach the transition. The speed of light, as the speed of information, resolves the paradox at the heart of our intuition. Light does not move infinitely fast because infinity would erase the very meaning of cause and effect. Light moves at c because c is the maximum rate at which information may flow. Yet another paradox remains. If light has no mass, why is it bound so strictly to c? Why must it move exactly at this speed, never slower, never faster? To answer that, we must examine the energy of the photon itself and the strange mathematics of momentum without mass. At first glance, it seems natural to think that something with no mass should have no resistance, no inertia, no barrier to motion. If mass is the anchor that slows things down, then the absence of mass might suggest perfect freedom, the ability to move at any speed, even infinitely fast. Yet this is not the way the universe works. Light has no rest mass, but that does not mean it is limitless. It does not drift lazily at any speed it chooses, nor does it leap instantly across space. Instead, it moves always and only at c, the cosmic speed limit. This is not a matter of preference, but of necessity, demanded by the equations that govern energy and momentum. The key lies in the famous relation that Einstein gave us, the connection between energy, momentum, and mass. Written in its full form, the relation says that the square of energy equals the square of momentum times c squared plus the square of mass times c to the fourth. This equation tells us the possibilities for all particles. If the mass term is non-zero, then the particle can exist at rest, with energy equal to its mass times c squared. As it accelerates, momentum adds to the total, and its speed approaches c, but never reaches it. But set the mass to zero, and the relation changes character. The mass term vanishes, leaving only the connection between energy and momentum. For such a particle, the only solution is to travel at exactly c. Any slower would demand a rest frame, but a massless particle cannot have one. Any faster would demand imaginary values of energy or momentum, which do not correspond to physical reality. In this way, the mathematics itself pins light to the cosmic limit. To be massless is not to be free, but to be bound. The photon cannot wander at half the speed of light, nor can it accelerate past the limit. It must move at c, always and everywhere. This explains why photons, from the moment they are born, travel at the cosmic speed. When an electron in an atom jumps to a lower energy level and emits a photon, that photon does not hesitate or accelerate. It is created already in motion at c. When nuclear reactions in the core of a star release photons, they are born moving at the limit. They may scatter countless times inside the dense plasma before escaping, but at each step of their journey, their local speed is c. It is not acceleration that brings them there. It is their very nature as massless particles. The same applies to all other known massless particles. Gluons, though confined within atomic nuclei, move at c when they are free, in theory. Gravitational waves, ripples of space-time itself, move at c across the universe. If there were any other truly massless particles, they too would follow this law. The speed of light is not really about light at all. It is about the only possible trajectory available to entities without mass. This realization resolves part of the paradox. To lack mass does not mean infinite speed. It means being bound to one speed, the ultimate speed. Massless particles cannot do otherwise because their energy and momentum leave them no choice. Light is free of weight, but it is not free of law. Its law is stricter than any faced by massive particles. Where we may move at many speeds below c, photons may only ever move at c. Their lack of mass is not liberty, but constraint. And yet, this constraint is what gives light its extraordinary role in the universe. By moving at c, photons carry information across space with absolute consistency. They define the shape of the light cone, the boundary of causality. They give us sight, memory, and knowledge of the distant past. Without this constraint, Without the inevitability of their speed, the order of the universe would falter. The paradox that once seemed a limitation is revealed as a foundation. Still, one might wonder, what happens in places where space-time itself is bent by gravity? Do photons still move at sea in those extreme conditions? Can they be slowed or sped up by the warping of reality around massive bodies? The answer requires us to step into curved space-time, where light bends and time itself dilates, yet the local speed of photons remains the same. That is the next chapter of the story, where gravity bends the path of light, but never alters the law of its motion. For something with mass, speed is a negotiable quantity. A rock can rest on the ground or fly through the air. A spacecraft can coast slowly or accelerate until it brushes close to the cosmic limit. Every increment of speed comes with a cost in energy, but the range of possibilities is wide. For something without mass, the situation is utterly different. A photon cannot stand still. It cannot linger in space, waiting to be pushed. It cannot choose to crawl or sprint. Its only existence is motion at sea. In this sense, the massless are more constrained than the massive. Their very being is tied to one velocity, as if space-time itself dictates their path from the moment of creation to the moment of absorption. This law is reflected in every corner of physics. In quantum electrodynamics, photons are the carriers of the electromagnetic force, moving at sea to transmit interactions between charged particles. In general relativity, gravitational waves ripple outward at sea, carrying information about catastrophic collisions in distant galaxies. These are not coincidences. They are the consequence of masslessness. In each case, the absence of rest mass forces the particle or wave to move along null geodesics, the exact paths permitted by space-time for entities bound to sea. It is important to emphasize that moving at sea does not mean infinite energy. Quite the opposite. For massive objects, approaching sea requires more and more energy, rising without bound as the speed increases. For massless particles, the energy is not infinite, but proportional to their frequency. A photon of visible light has a modest energy, while a photon of gamma radiation has vastly more, yet both travel at sea. Their difference lies not in speed, but in wavelength and frequency. The limit on speed frees massless particles from the burden of acceleration, but ties their identity to their energy instead. This is why light, though massless, still carries momentum. Shine a beam of sunlight on a solar sail, and the photons push it forward. This pressure is real and measurable. Photons may have no rest mass, but their energy and momentum make them capable of exerting force. This duality often surprises intuition. We equate mass with weight, with heaviness, with the ability to push. But light shows us that energy and momentum are enough. The absence of mass does not mean the absence of influence. The same principle underlies the photoelectric effect, where photons strike a metal and liberate electrons. The effect cannot be explained by waves alone, but by photons carrying discrete packets of energy. A photon with the right frequency has enough energy to free an electron, even though its mass is zero. Once again, the constraint of moving at sea reveals not weakness, but power. The paradox of weightless speed therefore deepens into elegance. The photon is not limitless. It cannot drift slower, cannot race faster. It is locked forever at sea. Yet within this constraint, it carries the universe's information, its energy, its momentum. To exist without mass is not to be empty, but to be bound in a very specific way. And so we come to the next question. If photons and other massless entities must always move at sea, how does this law hold in the presence of extreme forces, like gravity? When space-time itself bends under the pull of mass and energy, how do photons navigate those curves? Do they still obey the cosmic limit? The answer lies in the way gravity shapes not the speed of light, but the path it follows, bending trajectories without altering the local velocity. This is the subtlety of general relativity, where light speed remains constant even as space-time itself curves. The rule that massless particles must move at sea does not dissolve when the universe becomes extreme. Around massive stars, near neutron stars, and in the warped geometry close to black holes, photons still race at sea. What changes is not their speed, but their path. Gravity does not slow them down, the way air slows sound or water slows a swimmer. Gravity bends the space-time through which they move, and the photons, obedient, as ever, to the geometry, follow the new curves. This distinction is vital. When light curves around a massive object, as in gravitational lensing, its local velocity is still c. An observer falling alongside the photon would measure its speed as unchanged. But to a distant observer, the path looks distorted, the timing stretched, the signal delayed. This is not because the photon has slowed, but because space-time itself is warped. The geometry through which light travels is altered, and so the route and timing change. Locally, c remains absolute. Globally, the journey tells a different story. General relativity describes this with the concept of null geodesics. In curved space-time, these are the natural paths for massless particles. They are not straight in the usual sense, but they are the straightest possible routes allowed by the geometry. Around a black hole, null geodesics bend dramatically, wrapping into orbits at the photon sphere, or plunging into the event horizon, never to return. Yet in each infinitesimal step along the way, the photons still move at c. The limit holds, even at the edge of spacetime's most violent warps. This constancy is what makes relativity so powerful. Even in the presence of intense gravity, the speed of light remains the conversion factor between space and time. It is what allows the equations of general relativity to predict the bending of starlight, the delay of signals passing near massive bodies, and the rippling of spacetime by gravitational waves. All of these phenomena confirm the same truth. Massless does not mean limitless. Photons do not escape the rule of c, not in the vacuum of interstellar space, not in the grip of black holes, not in the expanding fabric of the cosmos itself. In this way, the paradox is resolved in full. Light has no mass, but that does not grant it infinite speed. Instead, the absence of mass binds it to the strictest of laws. Its speed is always c, never more, never less. Its energy and momentum carry influence, but its velocity is not negotiable. It cannot be still, and it cannot be faster. It is constrained by the very equations that describe the universe. And yet, this constraint is what allows light to be the messenger of the cosmos. By always moving at c, it gives us a reliable yardstick for distance and time. It provides the foundation for causality, the structure of relativity, the coherence of physics. The photon's lack of mass is not a loophole in the laws of motion, but the reason those laws appear so elegant. It is proof that to exist without mass is not to be free, but to be bound to the pulse of reality itself. Now we are ready to step into the next chapter, where gravity's influence on light takes center stage. For even though photons never outrun c, they live in a universe where space-time is curved by mass and energy. Their paths are bent, their journeys delayed, their histories written into arcs across the heavens. The bending of light by gravity is not a violation of the cosmic limit, but one of its most beautiful expressions, showing us how space-time itself sculpts the motion of the weightless. Light obeys the cosmic speed limit without exception, but its journey through the universe is rarely a simple straight line. In the presence of mass and energy, space-time itself bends, and light, ever faithful to the geometry, follows the curves. This bending is not the slowing of a traveler weighed down by obstacles. It is the redirection of a path by the shape of the landscape. Photons still move at c, but the terrain beneath them is warped. The first hints of this truth appeared long before Einstein. Newton speculated that gravity might bend light, just as it bends the paths of planets. But it was Einstein's general relativity that revealed the full picture. In this vision, gravity is not a force pulling on light, but the curvature of space-time guiding its path. Photons trace null geodesics, the straightest possible routes in a curved geometry. When space-time curves, those straight lines become arcs. Light does not deviate because it is tugged, but because the map it follows has changed. One of the most dramatic confirmations of this came in 1919, during a solar eclipse. Astronomers measured the apparent positions of stars near the sun's edge and found that they shifted, exactly as Einstein predicted. The starlight had bent around the sun, not because the photons slowed, but because space-time itself dipped in the presence of the sun's mass. It was a triumph of theory and a revelation of nature. Even weightless light feels gravity, not through mass, but through geometry. Today we see this bending on cosmic scales as gravitational lensing. Massive galaxies and clusters of galaxies warp space-time so strongly that light from more distant objects is deflected into arcs, rings, and multiple images. Telescopes capture these distortions, and from them, astronomers can map the unseen mass of the universe, including the elusive dark matter. Once again, the photons race at sea, but their paths curve like rivers winding through valleys carved by gravity. The speed is unchanged, but the direction is sculpted by the structure of space-time. This bending also carries with it a delay. When light skirts a massive object, the curve lengthens its path. Signals, passing near stars or planets, take slightly longer to arrive than they would through flat space. This effect, called the Shapiro delay, has been measured with exquisite precision, using signals from spacecraft and pulsars. It confirms again that space-time itself is the enforcer, stretching journeys not by slowing the photons, but by reshaping the geometry they must follow. Near black holes, the drama becomes even more intense. At the photon sphere, a ring located at 1.5 times the Schwarzschild radius, light can orbit the black hole in precarious circles. Any slight disturbance sends the photons spiraling inward or outward, but in principle, they can loop endlessly around the hole. At the event horizon, the curvature becomes so extreme that all paths lead inward. Light still moves at sea, but the geometry has sealed off escape. To an outside observer, signals from the horizon freeze in time, stretched and redshifted until they fade. Locally, the photon still obeys the same law. Globally, its fate is to be trapped. These effects highlight the subtlety of general relativity. Light never breaks the speed limit, but the structure of space-time ensures that speed alone does not determine what journeys are possible. A photon may still be bound, delayed, or redirected, not because it slows, but because the universe curves around it. Massless does not mean limitless. Even the weightless must bow to the shape of space-time. And so the paradox evolves once more. Light, which cannot rest and cannot move faster, finds itself bent and delayed, not by forces, but by the geometry of reality itself. The cosmic speed limit remains untouched, but the journey reveals the influence of mass and energy on the fabric of space and time. To see light curve around stars and galaxies is to see space-time itself made visible, traced in the paths of the weightless. Yet a new question waits at the edge of this understanding. If light can bend and delay in curved space-time, can it also be slowed in other ways? Can its speed through matter differ from its cosmic speed in vacuum? The answer leads us to a distinction between the true limit of c and the apparent velocities of light in media, where photons interact with matter but the universal law remains intact. Light's obedience to the curvature of space-time is one of the most beautiful consequences of general relativity. To watch a photon thread its way around a massive galaxy cluster, stretching into arcs and rings on a telescope's image, is to witness space-time itself revealing its shape. Yet for all this elegance, the constancy of the photon's speed remains. Locally, wherever you measure it, in whatever gravitational field it moves, the photon races. At sea, the bending is real, the delays are measurable, but the speed itself never changes. This distinction between local and global measurements is essential. Locally, meaning in a small enough region of space-time where curvature is negligible, the laws of special relativity apply. In such a region, all observers agree that light moves at sea. Globally, over vast regions where curvature matters, the path a photon takes may look bent or delayed compared to flat space-time. To a distant astronomer, the journey appears longer, the timing stretched, But this is not because the photon has slowed. It is because the geometry it followed was no longer straight in the Euclidean sense. Space-time has bent, and the photon has traced its natural geodesic. This plays out dramatically in gravitational lensing, where a distant quasar may appear as multiple images around a foreground galaxy. The light from the quasar took different paths through curved space-time, arriving at slightly different times. Some signals were delayed by years compared to others. Yet each photon, along its journey, still moved at c. The differences in arrival are written not in changes of speed, but in the geometry of the paths themselves. The Shapiro delay offers another vivid demonstration. When a radar signal is sent to a planet on the far side of the Sun, the travel time is slightly longer than it would be if the Sun were absent. The signal curves around the Sun's mass, and the extra distance translates into extra time. Precision experiments with spacecraft and pulsars have confirmed this effect again and again. The delay is not due to slowing, but to bending. Space-time itself adds the detour, and the photon, loyal to its law, traces it at c. Close to black holes, the interplay between light and gravity reaches extremes. Photons that venture near the photon sphere can orbit the black hole, caught in precarious loops. To an outside observer, this reveals itself as a glowing ring, the so-called shadow of the black hole, as seen in the Event Horizon Telescope's images. At the event horizon itself, light cannot escape at all. Locally, it still moves at c, but globally, the paths lead inward, and no signal returns. The geometry has closed in on itself, trapping light without ever breaking its speed. These effects remind us that the cosmic speed limit is not about preventing light from bending or delaying, but about preserving consistency. The photon is massless, and so it must travel at c, but the shape of space-time dictates where that path will lead. It may arc around stars, stretch across expanding space, or plunge into black holes, but it will never stray from the limit. The law is universal and absolute. Still, this raises another question, one closer to human experience. We know that light appears to slow down when it passes through glass, water, or other transparent materials. Fiber optics, prisms, raindrops, all reveal light moving at less than c. If the cosmic limit is unbreakable, how can light be slowed? The answer lies in the distinction between the universal law of c and the effective speeds that emerge when photons interact with matter. To unravel this, we must look beyond gravity to the subtle ways in which light dances with atoms and fields. The story of light in curved space-time reaches its climax near the most extreme objects in the cosmos. Around black holes, the bending of light is not a gentle deflection, but an overwhelming redirection. Photons that pass near enough may circle the hole endlessly in unstable orbits, painting the edge of the shadow we now capture with telescopes. Others spiral inward and vanish, their paths swallowed by the event horizon. To a distant observer, the light appears to slow, stretching into redder and fainter wavelengths as time itself dilates near the horizon. Yet for the photon, there is no hesitation, no slowing. It still races at c. The distortion is not in its speed, but in the fabric of time and space through which it moves. This distinction is crucial for understanding what it means to say the speed of light never changes. Locally, in every frame of reference, in every patch of space-time, no matter how curved, light moves at c. Globally, when viewed across long distances and warped geometries, its journey can look delayed, stretched, or even halted. But these effects are artifacts of perspective, not violations of the law. The photon itself never breaks stride. The cosmic limit is absolute. This constancy is why light is so valuable as a probe of the universe. When we measure how starlight bends around galaxies, we are not learning about the photon. We are learning about the shape of space-time itself. When we observe gravitational lensing, we map the distribution of matter in the universe, both visible and dark. When we record the time delays of signals skirting massive bodies, we confirm the predictions of relativity. Light becomes a tracer of geometry, a messenger, revealing not its own weakness, but the contours of reality. The beauty of this lies in the paradox it resolves. Light has no mass, yet it bends under gravity, not because it is tugged, but because it follows the only paths space-time offers. Its lack of mass binds it to C, but gravity bends its road without ever altering its pace. In this way, photons become both the most constrained and the most revealing of particles. Bound to a single speed, they still illuminate the richness of the cosmos by tracing the curves of space-time. And so the lesson of gravity is this: light is never slowed or sped by mass and energy, but it is guided, delayed, and sculpted by the geometry they create. To see the arcs of galaxies distorted into rings is to see space-time itself in action. To measure the shadow of a black hole is to witness geometry ruling over even the weightless. Massless does not mean limitless. Even photons bow to the shape of the universe. From here, the natural question is whether anything outside gravity can change light's pace. We know from experience that light travels more slowly in water, glass, and other materials than it does in vacuum. How can this be reconciled with the cosmic limit? The answer lies in the distinction between fundamental speed and effective speed, between the universal law of C and the apparent slowness that arises when light interacts with matter. This is where the story turns next, to the subtle dance between photons and atoms, where light can appear to slow, but the cosmic limit remains untouched. Everyday experience suggests that light is not immutable. We know it bends through glass, refracts in water, and slows inside fiber optic cables. Scientists have even managed to reduce its apparent velocity to walking pace within exotic materials like Bose-Einstein condensates. On the surface, this seems to contradict the cosmic law. If the speed of light is an unbreakable limit, how can we speak of slowing it down? The answer lies in the distinction between the universal constant c and the effective speeds we measure when light interacts with matter. In vacuum, light is pure. A photon moves at c, unencumbered, following the geometry of space-time alone. But when light enters a medium, it encounters atoms, molecules, and fields. Photons do not simply glide through as if nothing were there. They are absorbed and re-emitted, scattered and delayed, tangled in countless microscopic interactions. The beam continues forward, but the journey is no longer direct. The photon's local motion between interactions is still at c, but the signal as a whole, the group of photons carrying information, appears to move more slowly. This effective velocity is what we measure as the reduced speed of light in glass or water. This distinction becomes clear in the concept of refractive index. The refractive index of a material is defined as the ratio of c in vacuum to the effective speed of light in that material. For air, the index is close to 1, so light appears almost as fast as in vacuum. For water, the index is about 1 1/3, so light travels at roughly 2/3 of its vacuum speed. For glass, the index is even higher, and the slowdown more pronounced. Yet in each case, the photons themselves, between interactions, are still racing at c. It is the interruptions, the dance with atoms, that creates the illusion of slowness. The most dramatic demonstrations come from experiments with Bose-Einstein condensates, exotic states of matter, formed at temperatures near absolute zero. In such condensates, light pulses can be slowed to mere meters per second, creeping along at the pace of a human walk. Researchers have even managed to stop and store light, converting its energy into excitations of the medium, then releasing it again. To an uninformed eye, this might seem to overthrow relativity, but the truth is subtler. The photons that exist between interactions still move at c. What has slowed is the collective signal, reshaped by the medium's quantum properties. The cosmic limit remains untouched. This is why fiber optic technology works so reliably. Signals transmitted through glass fibers may take longer than they would in vacuum, but the limit of c still defines the maximum possible speed. Engineers can manipulate group velocity, dispersion, and delay, but they cannot make photons outrun the cosmic boundary. The universe preserves causality even in the heart of our technology. The key point is that the universal constant c is not negotiable. It is the speed of light in vacuum, the speed of all massless particles, the slope of causality in space-time. When we speak of slowing light in materials, we are not breaking that law. We are describing the effects of interaction, where photons hand off their energy to matter and back again, creating the appearance of slowness. The true speed, the heartbeat of reality, remains fixed. And so, the paradox clarifies. Light can be delayed, redirected, bent, and even stored, but it cannot be slowed in its essence. The cosmic limit is untouched, and causality remains protected. What we see in materials is not a challenge to relativity, but a reminder of the difference between fundamental laws and effective phenomena. The photon is still bound by spacetime's decree. It still moves at c. Yet this raises an even deeper realization. If light can be delayed without breaking the cosmic limit, then the speed of c is not merely a technical parameter. It is not just a value relevant to vacuum. It is the ultimate law of reality, immune to manipulation. No medium, no experiment, no technology can alter it. And this leads us to a new perspective. The speed of light is not about engineering or materials. It is about the structure of the universe itself. When light passes through matter, its apparent slowness is a story of interaction, not of defiance. A photon enters a medium like glass or water and is almost immediately absorbed by an atom or a lattice of molecules. That energy excites the electrons of the atom, which after a brief pause re-emit a new photon. The re-emission may not happen instantly, and the new photon may be emitted at a slightly different phase or angle. Multiply this process across countless atoms, and the wavefront of the light beam advances more slowly than it would in empty space. The photon has never once traveled slower than c in the intervals between events. It is the pauses, the detours, the endless dance of absorption and re-emission that delay the signal. This is why a prism splits white light into colors. The refractive index of a material depends on wavelength, so photons of different energies interact differently with the atoms they encounter. Blue light, with higher frequency, is slowed more than red light, causing the beam to spread into a spectrum. Each photon still moves at c in the gaps between atoms, but the ensemble appears slowed and separated. Once again, relativity is untouched, but the physics of matter leaves its mark on the journey. In extreme experiments with Bose-Einstein condensates, researchers manipulate these interactions with exquisite precision. By cooling atoms to near absolute zero, they create a state where quantum effects dominate. Light pulses entering such a condensate couple strongly to the atoms, effectively trading energy back and forth. The result is a dramatic reduction in group velocity, making the pulse crawl at human walking speed or even stop altogether. But this is not the same as a photon moving slowly. It is the collective wavefront being delayed by interactions, while each quantum of light, in the brief instance between handoffs, still races at c. This distinction between group velocity and fundamental velocity can be subtle. Group velocity is the speed at which the envelope of a wave packet moves, carrying information. It can be slowed, sped up, or even made negative in exotic media, but none of these phenomena alter the universal constant. No experiment has ever shown a single photon moving slower than c in vacuum, nor has any experiment sent information faster than c in any medium. The boundary of causality stands firm. Even the slowing of signals in fiber optics, which carry the lifeblood of modern communication, obeys this principle. The data moving through those fibers travels at about 2/3 the speed it would in vacuum, due to the refractive index of glass. Engineers account for this, adding repeaters and switches to maintain efficiency. But no matter how advanced the system becomes, the ultimate ceiling remains c. The photons may be delayed, but they never betray their cosmic law. What this reveals is the remarkable resilience of the speed of light as a principle. It is immune to manipulation. We can bend light with gravity, slow its signals with matter, store it in quantum media, and scatter it into colors, but we cannot alter its essence. C is woven into the foundation of space-time. It is not something matter can change. It is something matter must work around. This realization deepens our appreciation of the paradox. Light is not weakened by its interactions with matter, nor is its cosmic role compromised. Its apparent slowness in media only highlights the distinction between fundamental laws and emergent phenomena. The photon is bound to C, not by force, but by definition. Everything else, the refraction, the delay, the storage, is decoration, complexity layered on top of the unbreakable truth. And so, the experiments that seem at first to challenge relativity turn out to celebrate it. Every measurement of light slowed in matter confirms that C remains the unattainable maximum. Every delay, every refraction, every dispersion is evidence of light's constancy. We may sculpt the paths of photons, but we do not alter their essence. This brings us to a profound conclusion. The speed of light is not a problem to be engineered, not a barrier to be overcome, but a principle of reality. No material trick can change it, no clever experiment can bypass it. It is the pulse of space-time itself, the law that everything must obey. And from this perspective, the cosmic speed limit is not a constraint, but a definition of possibility. The constancy of C reveals itself most clearly when we look beyond the laboratory and into the universe. Across billions of light years, through expanding space and the pull of gravity, photons still keep to their rule. They may stretch into longer wavelengths as the universe expands. They may bend around clusters of galaxies. They may scatter in the thin gas between stars. But in every local measurement, their speed remains C. No amount of distance, time, or interaction changes this fact. What we call slowing is always an artifact of the environment, never a violation of the law. This is why astronomers rely so deeply on light as a messenger. When we observe a supernova exploding in a distant galaxy, we can trust that the photons we capture left that star at the same speed as the photons of a nearby candle flame. When we measure gravitational lensing, we can trust that the bending is due to spacetime, not a fluctuation in photon speed. When we observe gravitational waves arriving almost simultaneously with gamma-ray bursts, we confirm that spacetime's messengers, whether ripples in geometry or particles of light, obey the same boundary. This universality is what makes the cosmos intelligible. It also underscores why C cannot be treated as an engineering problem. The slowing of signals in fiber optics or in exotic media does not change the fundamental constant. It is like traffic on a highway. Cars may stop, pause, and restart, but the maximum speed of the road remains the same. Photons may pause in matter, may exchange energy with atoms, may be absorbed and re-emitted, but their intrinsic speed between events is unchanged. The group delay we measure is real, but the essence of C remains beyond manipulation. To attempt to change C would be to attempt to rewrite spacetime itself. The constants of the vacuum, the permittivity and permeability that define electromagnetism are not values engineers can adjust, like dials. They are properties of the universe. We can build lenses, fibers, crystals, and condensates to manipulate how light behaves within them, but the backdrop of reality remains fixed. This is why all of physics, from relativity to quantum theory, can rest on the same foundation. The cosmic speed limit is universal, and no medium alters it. Seen in this way, the slowing of light in matter is not a contradiction but a revelation. It shows us how photons interact with atoms, how waves and particles intertwine, how information flows through complexity. It demonstrates the richness of physics layered atop the constancy of geometry. The apparent slowness is the surface pattern, while underneath runs the unchanging pulse of C. And so the paradox resolves. Light can be slowed, delayed, redirected, even stored, but only in appearance. At its core, as a massless particle tracing the geometry of space-time, it remains forever at C. The law of relativity stands untouched. The slowing in media is a story about matter, not about photons. This understanding prepares us for the final frontier of speculation. If photons are bound so strictly, if space-time enforces its law so absolutely, could anything ever break the limit? Could exotic physics tachyons, warp drives, wormholes offer loopholes through which faster-than-light travel becomes possible? Or are these ideas illusions, dreams that stumble against the bedrock of causality. To answer, we must leave the realm of what has been proven and step into the domain of the hypothetical, where imagination collides with the limits of known physics. The cosmic speed limit feels unshakable, but human imagination has always tested boundaries. We dream of breaking chains, of finding loopholes, of reaching the unreachable. If c defines the maximum speed of causality, then the natural question is whether anything might slip past it. Could faster-than-light travel exist, not for photons, but for exotic forms of matter or geometry? Could we bend the laws without breaking them? Physics has entertained such possibilities, though always with caution. One of the most persistent ideas is the tachyon, a hypothetical particle that would always move faster than light. Unlike photons, tachyons would never slow down to c. They would exist only beyond it. Mathematically, inserting such entities into the equations of relativity yields strange results. Their energy decreases as their speed increases, and as they approach c from above, their energy diverges, just as it does for massive particles approaching c from below. They cannot cross the boundary. To exist at all, they must forever remain faster than light. But tachyons have never been observed. Every experiment searching for their signature has come up empty. For now, they remain a speculative artifact, a mathematical ghost rather than a physical reality. Another route of speculation lies in bending space-time itself. If geometry enforces the limit, then perhaps geometry could provide the loophole. This is the idea behind concepts like the Alcubierre warp drive. In this vision, a spacecraft would not move faster than light within its own region of space-time. Instead, space-time itself would contract in front of the ship and expand behind it, carrying the vessel forward like a surfer on a cosmic wave. Locally, no law would be broken. Globally, the craft could appear to outrun light. The mathematics of general relativity permits such solutions in principle, but at a steep cost. To create such a warp bubble would require exotic matter with negative energy density, something no one has ever observed. Without it, the idea remains theoretical, beautiful in its ingenuity but unreal in practice. Wormholes offer another imagined path. If space-time can curve and bend, could it also fold? A wormhole is a hypothetical tunnel connecting distant regions of space-time, a shortcut that allows signals to traverse great distances faster than light would in normal space. Like warp drives, wormholes appear in the equations of relativity, but keeping them open requires negative energy, the same exotic matter we have never seen. Without such material, wormholes collapse too quickly for anything to pass through. With it, they might exist, but we have no evidence that the universe tolerates them. The common thread in all these ideas is that faster-than-light motion is never about exceeding c in the usual sense. It is about reshaping the geometry of space-time so that the journey changes. The cosmic speed limit is not overthrown. It is skirted by bending the rules of distance and time. Tachyons, warp drives, and wormholes all avoid saying that a particle simply outruns a photon. Instead, they propose that space-time itself might allow paths that look like shortcuts. But each proposal requires conditions or materials that physics has not confirmed. Speculation pushes us forward, but evidence keeps us grounded. So far, no experiment, no observation, no particle collision has revealed anything that exceeds the cosmic speed limit. Gamma-ray bursts from distant galaxies arrive in perfect synchrony across energies, confirming that photons of different frequencies all travel at the same c. Gravitational waves and light from neutron star mergers reach us together, confirming that space-time's ripples and its messengers obey the same rule. Nature has shown no crack, no exception, no hint of a loophole. And this brings us back to the paradox in a new light. If faster-than-light travel were possible, the consequences for causality would be profound. Effects could precede causes, information could loop backward in time, paradoxes would abound. Relativity resists such outcomes, not as a suggestion, but as a necessity. The limit is not simply about speed, it is about preserving the coherence of time. To imagine breaking it is to imagine unmaking the order of the universe. Yet the temptation remains. What if, somehow, the constants of the universe allowed it? What if negative energy exists, or space-time is richer than we know? These questions propel physics forward, not because the answers are near, but because the boundaries they test remind us of what is at stake. To ask if C can be broken is to ask whether causality itself is negotiable. So far, every sign tells us it is not. But before we dismiss the dream entirely, we must explore these hypothetical constructs more carefully. Tachyons, warp drives, wormholes. What do they really mean? What would their existence demand of the universe? And why, despite their allure, does nature appear to deny them? The idea of tachyons is seductive because it seems to flip the rules of relativity on their head. If massive particles are forever stuck below C, and massless particles are bound exactly to C, then perhaps there exists a class that lives beyond C. At first, the mathematics seems to allow it. Insert an imaginary rest mass into the energy-momentum relation, and faster than light speeds appear possible. But the price is steep. Such particles would destabilize quantum fields, triggering runaway processes that would make matter itself unstable. Even if tachyons existed, they would not behave like usable messengers or vehicles. They would unravel the consistency of the vacuum. The fact that no experiment has ever revealed a tachyon is perhaps less a disappointment than a reassurance that our universe is not built on unstable ground. Warp drives push the imagination in another direction. Rather than trying to make matter move faster than C, they ask whether space-time itself can do the work. In principle, relativity allows space-time to expand faster than light, as we see in the early universe during cosmic inflation. Galaxies recede from us at effective velocities greater than c, not because they move through space faster than light, but because space itself expands between us and them. The Alcubierre drive borrows this concept, imagining a bubble where space contracts in front and expands behind, sweeping a craft forward. Locally, the ship never breaks the speed limit. Globally, the journey looks faster than light. But here, the demand for exotic matter returns. The equations require negative energy density to sustain the bubble, something ordinary matter cannot provide. Quantum theory permits negative energy in fleeting, tiny amounts, as in the Casimir effect, but not in the vast quantities needed to drive a starship. Without a supply of exotic matter, the warp bubble remains a dream. Even with it, the bubble poses challenges: instability, destructive tidal forces, and the possibility of horizons trapping the travelers. The mathematics permit speculation, but nature offers no hint of realization. Wormholes carry a similar allure. They offer the possibility of shortcuts, of tunnels through space-time, connecting distant points. General relativity's equations contain such solutions, known as Einstein-Rosen bridges. Yet, in their natural form, these bridges collapse instantly, pinching off before anything can pass through. To hold them open requires, again, negative energy. With it, they might allow travel not only across space, but across time, raising the specter of paradox. A traveler through a wormhole could return before they left, undoing the order of cause and effect. For this reason, many physicists suspect that even if wormholes exist, some deeper law of quantum gravity would forbid their use for faster than light travel. Despite these obstacles, the fascination persists. Science fiction thrives on warp drives and wormholes because they capture our yearning to defy distance, to conquer the vastness of space. They are metaphors as much as possibilities, reminding us that imagination runs ahead of evidence. Physics does not dismiss them outright. It explores them as thought experiments, tools for testing the boundaries of relativity and quantum theory. In doing so, we learn not only about what might be possible, but about why the universe protects its consistency so fiercely. The silence of nature is telling. Every photon we measure, every gravitational wave we detect, every cosmic signal that reaches us affirms the constancy of C. Distant explosions arrive with light and gravitational waves locked in step, confirming that space-time admits no exceptions. Cosmic rays, traveling for billions of years, arrive, still bound by the same law. The universe has had every opportunity to reveal a crack in the speed limit, but none has appeared. The cosmic enforcer holds steady, and so we return to the heart of the paradox. The dream of faster-than-light travel is less about physics than about our longing to overcome scale. The universe is vast, and c makes it feel larger still. But that vastness is not an accident. It is the price of consistency, the cost of causality. To break c would be to unmake order, to dissolve the coherence of time itself. For all our speculation, the evidence tells us the dream will remain a dream. Yet one more step of reflection remains. If nothing can truly break the limit, what lesson should we take from it? What meaning lies in the fact that c is unyielding, that light and causality march together at the same pulse? The answer takes us to the final chapter of the paradox, where the limit is not a frustration, but a revelation of what time itself, island. The possibility of breaking the cosmic limit always circles back to paradox. If a signal could outrun light, then causality itself would unravel. Imagine a spacecraft capable of traveling faster than c. In one frame of reference, it departs after noon and arrives before noon, turning arrival into a cause and departure into an effect. Imagine a message sent across space that reaches its destination before it was transmitted. The chain of cause and effect collapses into contradiction. Relativity resists this, not as a matter of convenience, but as a matter of survival. Time itself depends on the order of events, and that order is guarded by the boundary of c. This is why every proposal for faster-than-light travel runs into deep conflict with causality. Tachyons imply signals that can travel backward in time. Warp drives and wormholes suggest shortcuts that permit closed time loops. The mathematics does not forbid such paths outright, but it warns us of their consequences. Paradox is not a puzzle the universe is likely to tolerate. If physics has a hidden safeguard, it may be that these exotic possibilities are prevented not by improbability, but by impossibility. Negative energy may never exist in usable amounts. Wormholes may always collapse. Warp bubbles may always destabilize. The cosmic speed limit may be enforced not only by relativity, but by the deeper, still undiscovered rules of quantum gravity. And yet, speculation remains valuable. Even if tachyons and warp drives never materialize, they sharpen our understanding of why the speed limit matters. They show us that c is not simply a number, but the slope of space-time, the heartbeat of causality, the definition of what it means for one event to follow another. To break c would not simply be to travel faster, it would be to undo the meaning of time itself. That realization, though sobering, is also profound. The dream of surpassing light speed is unlikely to vanish. As long as the stars remain distant, imagination will conjure shortcuts. But physics offers us a different kind of wonder. Instead of chasing loopholes, it invites us to marvel at the fact that the universe is coherent at all, that the same photons born in distant galaxies obey the same law as the ones emitted in a laboratory laser, that the same constant c governs both the flicker of an atom and the structure of space-time itself, that across scales so vast they defy comprehension, the order of cause and effect holds unbroken. Perhaps that is the true lesson of the paradox. The speed of light is not a barrier we are meant to conquer, but a truth we are meant to recognize. It is not the enemy of exploration, but the foundation of understanding. It gives the universe its shape, its order, its rhythm. It protects the arrow of time, the coherence of history, the possibility of knowledge. To long for faster-than-light travel is to long for escape, but to accept c is to embrace the universe as it is, vast, consistent, and deeply intelligible. And so Chapter 9 closes with a recognition. The cosmic speed limit has not been broken, and likely never will be. But in its unyielding constancy, it reveals something greater than possibility. It reveals the nature of time itself, and it points us to the final chapter of this journey, where the meaning of the limit becomes clear. The journey that began with a paradox now arrives at its conclusion. We asked why light, weightless and massless, does not race infinitely fast, why it is bound instead to a finite velocity of 299,792 kilometers per second. We followed the trail through relativity, through space-time geometry, through experiments that slowed light in matter and theories that imagined breaking its limit. Again and again, the same truth emerged. The speed of light is not a property of photons alone. It is a property of the universe itself. To understand this, imagine stripping away all particles, all fields, all matter. What remains is space-time. Even in that emptiness, C still exists. It is woven into the equations of relativity, into the relationship between distance and duration. It is the conversion factor between space and time, the number that turns seconds into meters, events into intervals. Light happens to travel at c because it is massless, but the constant would exist even if light did not. C is not the speed of light. Light is the speed of c. This realization reframes the paradox. To ask why light is not faster is to misunderstand what speed means in the universe. Speed is not an arbitrary number. It is defined against the backdrop of c. Nothing can move faster because faster has no meaning. Faster than light would be like trying to turn north of north, to stretch beyond the definition of direction itself. C is not a limit imposed from the outside. It is the boundary that defines what motion, causality, and time can be. This explains why C appears everywhere in physics. It governs the propagation of electromagnetic waves, the rippling of gravitational waves, the behavior of neutrinos, the interactions of quantum fields. It sets the stage for causality, determining which events can influence which others. It defines the shape of light cones, the architecture of space-time itself. Without it, relativity would collapse, causality would dissolve, and time would lose coherence. Seen this way, the constancy of light's speed is not a weakness, but a triumph. It is the reason we can know the past, predict the future, and trust the order of events. It is the reason the universe is not chaos but cosmos. What once seemed a paradox turns out to be a clue, pointing us toward the deepest truth, that reality itself is structured by a universal rhythm, a pulse that binds space and time into a coherent whole. The meaning of the limit is not about denying possibility. It is about preserving coherence. Without C, there would be no causality, no time, no physics, as we know it. The photon's obedience to the law is not constraint but testimony. Every beam of light, every ripple of gravity, every messenger racing through space-time is a reminder that the universe has order. And so, the final image emerges. Light, weightless and massless, bound to C, not by weakness, but by necessity. Space-time itself, enforcing its geometry with unyielding law. Causality, protected by the constancy of the cosmic speed limit. And us, witnesses to the paradox, now seeing it for what it is, not a riddle, but a revelation. Yet there remains one final reflection. If C is not just the speed of light, but the heartbeat of the universe, what does that mean for our place in it? The meaning of the limit deepens when we think about our relationship to it. Every journey we take, every signal we send, every glance we cast into the night sky is shaped by C. The light that reaches us from a distant star began its voyage long before our species even existed. The photons travel unerring at C, carrying with them a memory of ancient events, and when they arrive, we call it astronomy. In truth, it is archaeology across space-time, the study of history carried not in books but in beams of light. Without the limit, without the constancy of that speed, the story of the cosmos would not be readable. It is precisely because light travels at a fixed rate that distance becomes time, and time becomes knowledge. C also teaches us humility. The universe is vast beyond imagination, and C tells us that much of it will always be beyond our reach. Even at the ultimate speed, crossing to the nearest stars takes years. Reaching the center of our galaxy takes tens of thousands of years. Traveling across the observable universe would take more than 10 to the power of 10 years, far exceeding any scale of human history. These numbers remind us that exploration is not simply a question of engineering, It is a question of perspective. We are small creatures, bound by the great pulse of space-time. And yet, within that bound we find wonder. Philosophically, the limit is also a boundary between the possible and the impossible. It reminds us that freedom, without structure, is incoherence. Just as music requires rhythm and architecture requires foundation, physics requires C. The very notion of cause leading to effect, of the future following the past, depends on the limit. To live in a universe without it would be to live in one without order. Our minds, our sciences, even our sense of identity depend on the stability that C provides. The constancy of C also bridges the deepest theories of modern physics. In special relativity, it unifies space and time into space-time. In general relativity, it becomes the messenger of geometry, defining how curvature guides motion. In quantum field theory, it sets the pace of interactions, linking energy to momentum. Even in speculative frameworks like string theory or ADS-CFT, C is present as the fundamental speed of information. Wherever we look, the same constant waits, reminding us that no matter how strange the mathematics, the pulse of reality does not change. This is why the speed of light is often described as sacred in physics, though not in a mystical sense. It is sacred because it is universal, because it is unyielding, because it binds together concepts that otherwise would drift apart. It is sacred because without it, the universe would be unrecognizable. And so we learn that the paradox of weightless speed was never a paradox at all. It was an invitation to rethink motion, to redefine speed, to understand causality. We began by asking why light, massless and free, did not move infinitely fast. We end by realizing that masslessness does not mean freedom. It means obedience to the deepest rule of space-time. The photon's limit is our limit too, and in that shared boundary lies the meaning of reality. But one final reflection remains. If C is the heartbeat of the universe, what does that say about time itself? Is time an independent flow, or is it nothing more than the unfolding of causality at the rhythm set by C? This is the final question, the last horizon of our journey. Time has always been the most mysterious companion of the speed of light. From the moment Einstein revealed that space and time are bound into one fabric, C became more than a speed. It became the stitching that sews the two together. Without it, seconds and meters would have no translation, clocks and rulers would float unconnected, and the geometry of reality would dissolve. The constancy of C tells us that time is not an independent river, nor is space an empty stage. Together, they form space-time, and C is the conversion factor that allows them to speak the same language. When we say that nothing can move faster than light, what we really mean is that nothing can outrun causality. C defines the edge of influence. An event can affect only what lies within its light cone. Outside that cone, the event is silent, unable to reach, unable to touch. This structure of light cones, stretching from every moment, gives time its arrow. The past is what lies inside our cone, the region from which signals could reach us. The future is what lies ahead, the region we can influence. Causality is the architecture of time, and C is its measure. To dream of faster than light travel is to dream of breaking free of this architecture. But that would mean unbinding cause from effect, dissolving the order of time itself. Relativity protects us from this collapse by making C absolute. Every photon obeys it. Every gravitational wave traces it. Every field and particle aligns to it. C is the ultimate enforcer, not of speed, but of coherence. From this perspective, the meaning of the limit is clear. It is not a ceiling that frustrates our ambition. It is the ground that makes existence possible. It is the universal rhythm that ensures the universe has a past, a present, and a future. It is the law that ensures actions have consequences, that memory is real, that knowledge can persist. The photon's unwavering speed is not a constraint, but a gift, and so our story closes. Light, though massless, does not move infinitely fast. It moves at c, the constant that defines space-time itself. Its obedience to the cosmic limit reveals not weakness but necessity. It shows us that massless does not mean limitless, that gravity bends but does not slow, that matter delays but does not alter, that speculation inspires but does not break. Above all, it shows us that the speed of light is not truly about light at all. It is about time, causality, and the very possibility of a coherent universe. The last image is of light itself, streaming across the cosmos, tracing the geometry of space-time, carrying with it the memory of stars long dead, galaxies still forming, and the origins of everything we know. It does not race infinitely fast. It does not arrive instantly. It moves at c, the eternal rhythm of reality, the pulse of causality, the boundary between the possible and the impossible.